So we will start with dislib. Okay. I will present an overview of the dislib. Then I will present the basic data structure that the dislib has, the DS array. Then we will go through some basics on machine learning and estimators, just that those that maybe are not that familiar understand a bit more. And then we will explain a bit the typical workflow that we follow in the dislib. And then I present some results, so just that you see that this is going quite well. And a sample code to show you a bit the internals of a sample code. Okay, in this case, I choose the Cascade support vector machine. And then we will browse a bit the dislib website so you can see what you can find there. Okay, so the dislib is a parallel machine learning library. Okay, basically we started developing some machine learning codes at a given moment. One of our colleagues that actually is not at BSc, Javier Albert, decided that maybe it would be a good idea to collect them into a single library. Okay. So we started to develop this set of algorithms, all of them with a unified interface. And for this, he inspired on the scikit-learn library, which is very popular for people using machine learning, okay, and has these basic methods of fit and predict. So we will see this in the examples. Then he designed this distributed data structure with the collaboration of us, that is DS array. Okay, we'll explain a bit how is this array organized in the next slide. And then we have some unified data acquisition methods also. And the nice thing about the dislib is that the parallelism is hidden to the end user. Okay, we use PyCOMPSs and the tasks and the different aspects that has been presented in the morning, but this is in the library, so the user does not need to learn that much about PyCOMPSs. Okay, and it's open source and available to the community, providing what I said, multiple methods for initialization of data, both automatically or by reading data from different formats, so on. Has methods for clustering. We'll have examples today with the k-means and the dbscan. Also have methods for classification. We will see today the Csvm, the Cascade support vector machine, and also the random forest. Methods for model selection that we will see also an example, and so on. So the basic data structure that is used in the dislib is called the DS array. Okay, basically it's a two-dimensional structure that decomposes the data, two-dimensional data, into multiple blocks. Okay, so given a matrix that have as rows the samples and as columns features, what we do is we divide this in blocks. Okay, so you give when you initialize your data, either by reading or with methods to initialize them automatically, you give the block size. So we will discuss a bit more about how to define the block size later. No? That have a given number of rows and a given number of columns. No? So then these blocks are Numpy Arrays. So we leverage the Numpy library for all the data management operations. Okay. So then these blocks don't need to be in the same node of a distributed computing platform. So what does this mean? That well, in this case we have 5 by 3. So it's 15 blocks. So imagine that this fits in the memory of one node. So we can have 15 nodes, each of them hosting one of these blocks and doing operations, in this case, tasks from PyCOMPSs in parallel in these blocks. No? So this is a small example, but of course you can have also multiple blocks in a single node, okay, and reading. You don't need to have them all at the same time in memory. Okay, the constraint will be that one block fits in the memory of a node. Okay, which usually is quite big, a big block. Okay. So then, besides this, that I've told you a bit the internals, you can work with a DS array if it was a regular Python object and using the regular methods that you will use, for example, for Numpy Arrays. Okay, and the difference is that it's not stored in the, not all the array is stored in the main memory of the local node, but it's stored in distributed fashion, and also it doesn't need to be stored in memory all the time. So because we serialize the data, we read and write the blocks that are in memory between tasks. So we don't need to have all the array in memory. No? And you will see that you have methods for instantiation and for slicing using the same syntax as the Numpy arrays. And these methods also internally are parallelized with PyCOMPSs. So it's not only the methods like the clustering or classification methods that are parallelized, but also the different operations with the data, like loading the data or indexing or other operations. For example, we have not all possible operations, but you can have operators like the min or transpose, for example, that are internally parallelized with PyCOMPSs. Also, the DS arrays have another characteristic, is that they can be iterated along both axes. So you can, the internal code of the dislib uses this a lot in most of the methods. No, it goes through the different blocks of the DS array using iterators. And then also you can represent the same way that you represent the samples, you can represent the labels using another distributed array. Okay. Well, then a bit about the different methods. A lot of you probably will know that you have different type of machine learning methods. You can have unsupervised methods where you can find patterns from data that has no labels. We will see an example in the next slide. So typically you do this with the clustering, for example, or supervised methods that learns a given function, a given decision function from labeled data, data that has already been inspected somehow. And an example of this is classification. Okay. We have here an example of clustering. Okay, we have the original data on the left, the two-dimensional data. Okay, where we have these dots, and initially the user may not know anything about this data. Okay. So for example, with clustering, we can classify them on 3 different groups and find the center of this group, okay, which also will characterize the cluster. So then when we want to predict another point and see if it's in one or the other cluster, we will use this information, like the distance to the center, to classify it in a given cluster, for example. No? And from this, we start from unlabeled data. We only know the position of the points. But you can have other type of data. In this case, is also a set of points with 2 dimensions, but maybe that there you have some label on it. No, then you have red dots and you have blue dots in this case. No, so these dots have some characteristics, whatever. We don't know, can be temperature, can be distance, can be if it's black or white, whatever, different labels, okay? And then you can use classification algorithms to define somehow these regions, and later also predict for a given point if you will label on one area or in the other. So typically use this with classification methods. Okay, then we have the estimators that we use, or methods that we use in dislib. As I said, are based on scikit-learn. So it's not that we cover all the scikit-learn library, but we have some of the methods that the scikit library has. Okay, and it has the same look and feel. Okay, And here, what is an estimator? So anything that can learn from data, no? Label it or unlabel it, like the clustering methods or classification methods. And in scikit-learn, typically, if those that you are familiar with it will know, has two main methods. The fit method that given some input data, usually then you pass to this method the trained data, it will learn from this data. No? For example, the fit of the clustering, no? Will, given the points, will decide how many the clusters and the center of the cluster. No? How many depends on the actual algorithm. For some algorithms, you give the number of clusters. No? And then the predict is once you have already the function that it returns from the fit, no? the trained model, okay, you can use it to predict with new data. No? Typically, then we talk about the test data. That then we can use the test data to predict whatever to which group belongs, to which cluster belong, or to which label will have whatever, based on this predicted with the computed model that we have before. And here we have an example, no? The typical workflow that looks very similar to what you will have in scikit-learn, okay? For example, first we read the data from files. In this case, we read from text files. And an observation here is that we give the name of the file, in this case, a CSV file, but also we give the block size, okay? Because X here, X, is going to be a DS array. So what will be, how we will store this trained data in memory? We will do blocks of 10 rows and have 180 columns, okay? And we will create as many blocks as necessary, okay? And then we will store this, or we will divide this in the blocks, and if necessary, we will upload the different blocks in the memory of the distributed computing platform. No? If you do this already, we do this already in a distributed computing platform. So already the reading and creation of the blocks is done in parallel. Okay? And here for the test, we have the same block size, for example, but in this case, normally a smaller data set. Okay. Okay, then when you have load the data, you can instantiate an estimator. In this case, is the k-means. And for this algorithm, it's one case when you typically give the number of clusters you want to find on your data. Okay, so you are instantiated here the k-means estimator. Okay, so, and you give the parameters. Then you can fit using the trained data X. Okay, so you pass X to the method fit. Internally, this again is parallelized with PyCOMPs, as I said before. Okay, and then you can predict with the test data. Okay, and later you can check if how well went the prediction or what the accuracy, etc. No? Okay, so this is the typical flow. Okay. And as I said, most of the methods, not instantiation usually, but most of the methods are parallelized internally with PyCOMPs. For example, the k-means in the dislib is not exactly the same that you have seen in the morning, but it's similar internally to the one we saw in the morning. Okay. Okay, some of the methods that are supported right now. We have multiple functions to create the DS arrays from random data, existing data, from files. This is something also that we are extending it. No? So if we have an application that is using the dislib and requires a given data format, so we try to adapt to our users and to add it to the library. No? Then you have other functions to access the arrays, to scale, to apply a function. For example, this can be a function that internally does a lot the dislib. No? Imagine you have to do a given operation on the whole DS array. So then this is converted into apply this function to each of the blocks of the DS array, for example. No? So we have functions to do this in a more automatic way. Then we have the estimators for matrix decomposition. We have the principal components analysis that given a larger data set with multiple variables is able to determine which are the variables that are more important, no, in the behavior, so influence more in the behavior of the data set. We have clustering methods besides the k-means that we talk about it, that needs, for example, needs to have the number of centers that are required. dbScan is another example that besides, we will see in the hands-on, the difference a bit between k-means and dbScan, why it's better some cases dbScan and others is better k-means. Gaussian mixture, it can be seen as a clustering, but also what it does is generates a set of Gaussians, no, of distributions that represents the data. And another that we recently added, for example, is Daura, that it's a clustering algorithm that comes with a molecular dynamics package that is called GROMACS. Okay, so this is the same clustering that was defined by Daura, is the researcher that proposed it, has been implemented on top of dislib. Okay. For classification, we have the Cascade support vector machine that I will describe it in the next slides with a bit more detail. And we have also the random forest. For recommendation, we have the alternating least squares. That is the recommendation algorithm that was initially proposed by Netflix. We have also the linear regression. For regression, we have for network queries, we have the k-nearest neighbors. And for model selection, we will see an example of this. No? Model selection is, I told you before, no, that for example, for k-means, you need to pass the number of clusters that you want to do the clustering. No? And for other, we'll see that for other methods like Cascade Svm or dbScan, you need to pass some parameters. Okay. So then the grid search is useful, or the model selection in general, is useful to define these initial parameters. So you can, then it runs the algorithms a number of times, testing with multiple parameters, and then it gives you the result which of these parameters is better. Okay? So we have two versions, grid search and randomized search implemented. Okay, so the dislib is not only the library and we are looking for users and so on, but it's also a research project. Okay, so we have been comparing and collecting some papers, and in this case, these results compare the k-means from the dislib, and you can see the results in blue, against two other libraries that are quite popular. One is DaskML, which internally is parallelized with Dask, which is also a task-based approach, or the MLlib, which is the machine learning library from Spark. Okay, so in this case, we run for these k-means with different data sets. Okay, for this case, with the 1 million samples and 150 features, for example, we have here time. Okay, and time, so less is better. We can see that the dislib in this case, it's always running faster than DaskML. Okay. I'm not showing here the results for MLlib is because for this problem, MLlib was not able to give results because of the memory issues. So even we were trying with different sizes for any of these, they could run for this data set. Okay. Here we have another case with 500 million samples and 100 features. For this, MLlib was able to run with 768. This is 1, 2, 4, 8, 16. This is 16 nodes of Mare Nostrum and 32 nodes of Mare Nostrum. So with this number of nodes, was able to find a solution. Okay, but not with a smaller, because we were not fitting the amount of memory that MLlib was requesting was too large to get the result. No, so the application was failing. And we see that in all these cases also dislib is going faster. Okay. And here we have a case with these 2 billion samples and 100 features that neither dislib nor mlib were able to run with any of these configurations that we were running. Okay, so we have no comparison because of this. We're not able to run. Okay. Then next I would like to present is a bit the internals of how is this parallelized. Okay, I took a code that is not very intuitive. Okay, but okay, this was the one that I thought was maybe easier to understand. No? So the Cascade support vector machine is a parallel implementation of the support vector machine learning algorithm. Okay. In this case, what this Csvm does is it splits the training data set into multiple chunks. Okay. And then it calls to a support vector machine for each of these chunks. Okay. In this case, we will leverage then we will see that we will leverage the SVM, the basic method from scikit-learn to pass a block of in this case a block of the DS array and call the SVM of scikit-learn to solve this problem for a small chunk. Okay. Then the overall algorithm merges the different results. Okay. And then this is used to train again until a given convergence factor is obtained. Okay, so the method is iterative. So at each iteration, we do this split of the data in different chunks. We call the individual smaller SVMs, and then we combine the results and so on. Okay, so this is the main code here in the first block on the left. Okay. So you see this now, we have this check finish. This will be the convergence factor. Till this is not met, we do these iterations, okay? And then we check the convergence, okay? So this 2 iteration is what is done inside the while, okay? And then it first partition the data. So you here see we pass the inputs X and Y, and we partition these in different blocks, okay? And then it combines, it creates tuples of a part of X and a part of Y, okay? And this is what is passed inside this for loop, okay? And this is then passed to this train function. We will see this, what is this train later, no? And then this is not, in one iteration, this is done multiple times. Also here we have another invocation to train, and even there was another one that I did not copy the text, but basically to understand is that we are partitioning the data, as I said, and training, okay, the chunks that we have created, okay, and then we do some combination with the results. And this train here that I was calling, this one is a task, okay. So you can see here that the train is a task, has some input, a collection, another collection, another collection. Okay, in this case, the depth is the profundity till the depth till depth is the same, no? Till so the level till the runtime will look into the elements of the collection for looking for the dependencies. Okay. And it returns 4 values for different values. No? And you can see here, no, inside, besides some management of the data, basically what it does is creates an instance of the support vector. Sorry, SVC, but is the SVM, okay, from scikit-learn, okay. I don't know why it's called SVC, but you see here from SQL SVM SVC. I don't know why he put SVC. It's a bit misleading. Should be SVM. And then it goes to the feed method of this SVM. Okay, so we are fitting chunks of data in each of the tasks. Okay, and this will be the sample code. No, this is the internals. This is the code of the dislib. Okay, but all these trains and all this internal code is not seen by the user. but the user will write this user code, okay? Or in the examples, we will write this user code. We do the corresponding imports, okay? Then in this case, for example, we load the data with from a special data file format, the Svm Lite, which is a library, specific library of SVMs, okay? So we read this data with this block size, 5,000 by 22. And well, here it needs also to know the number of features, okay? And well, this is another option, okay? It creates an instance of the Cascade Svm with some parameters, okay? I will not go into the detail of the parameters, okay? And then it calls the feed of this data, okay? So this is a user code. And then internally, for example, this was not, I think it was for this data, yes. This is how it's run in my machine, for example. This is a trace file, okay? So if each of the rows represents a core, and so we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rows, 10 cores executing at the same time, okay? The different colors represent different tasks. In this case, we can see here the ID, the name of the task, okay? We have some data operations at the beginning, like the read Svm Lite, no? So this original Svm Lite that we were invoking as a single call internally is parallelized, in this case, in 10 tasks, okay? Well, then we have some other auxiliary tasks, okay? And then the train, you can see this is the train. You can see in this case, the train has some load imbalance. Some of them are taking longer than others. This can happen, no? Even we are dividing the data into chunks of the same size. It may happen that sometimes the duration of the tasks can be longer than others, but each of these groups that we can identify that at the start at the same time are iterations, no? So the iterations we saw here on the train, on the do iteration, okay? Each of them is one iteration, and we have multiple iterations, okay? And this is the task graph. I'm not showing the whole task graph because it was very big, okay? But you can see at the beginning the tasks that do the read in blue, and then you have, well, the other auxiliary tasks that we had, the red and white, but then the pink, all the other pink tasks. And here we can see the data dependencies. No, we can see that it's quite wide, so has some parallelism, but also has some dependencies between them, okay? So there are tasks that need to wait for other tasks to finish before being started, okay? And so here we have the different iterations that we were seeing before. This is one iteration, this is another. So in fact, the load imbalance here, I'm not showing here, but when we have larger lines here is because in fact, this is composing multiple tasks. These are multiple tasks that are run one after the other, okay? Although we cannot appreciate in this view, okay? And well, this is a smaller zoom of the beginning, no? So you can see a bit better the different tasks and the different structure of the data graph, okay? The task graph. The task graphs you have seen this morning that you can visualize it, but also it sometimes can be very big, okay? So be careful when we try to visualize the task graph. Especially if you're using the Docker. In my case, I have difficulties on visualizing the Docker, the task graphs running the Docker because it takes a lot of time, okay? Unless it's a small example, it may happen that it gets stuck in the generation. Okay, so next what I wanted to do is to browse a bit the dislib. So you can see, let me open the browser. So the website, if you want to go, is dislib.bsc.es, okay? You can see now in in the screen, no? So how it's organized? Well, you have two different tables of content, but well, we can go first through the main website. You can see here, beside the tables of content, we have some comparisons of results in Mare Nostrum 4. In this case, are run always with 8 worker nodes in Mare Nostrum. Each of the nodes in Mare Nostrum have 48 cores. So this is like almost 400 cores to run each. And we run with 2 different configurations. I think we will explain this tomorrow. GPFS is when you leverage the shared file system of Mare Nostrum, or Scratch is when you are not using the shared file system and you copy the data into the local disk, okay? And it's comparing multiple algorithms between the 2 options, no? When you use GPFS and when we don't use it, with all these different algorithms, most of them with data sets that are proposed in the community, like this KDD or Netflix, MNIST, are data sets that are available from multiple data sources. Okay. You can also go to the source code, and for example, if you want to look a bit more into this Csvm that I was showing you, if you go to classification, and then Csvm, and then you can open. So the code is quite well organized. If you want to browse it and have a look, you have here, for example, this is the code I was showing in the slides. I copied from here. And also, you have here, more interesting for you today in the tutorial, is the user guide, okay, which explains a bit the different aspects of the dislib. There is some interesting text here about choosing the size of the block size. So although we claim that using the dislib can be simple, determining the block size maybe is not that intuitive, no? So here gives some hints on how to define the block size, okay? And then, well, you have some more information here about the different methods, whatever. And the other part that we will use later in the hands-on is the API reference, okay? Here you have for all the methods, for example, the Csvm that I was showing before. You go here, you have the class, you have the instantiation, you have the different methods that you have, the fit, the predict, whatever. Okay, the score, we will see also that we will use the score to determine the quality of the return of the result, okay? So you can go here during the hands-on, I will ask you to go here to look at the documentation, okay? Vale. Then this is then what I wanted to explain. You have also some more information here, okay? Well, this is general for COMPSs also, okay? So, but you have it here, okay? Okay, so then with this, we will move now into the.
Sorry,
Yes,
Rosa.
sorry. Sí.
There's a question in the chat before going. Paolo Marangio is asking, are neural networks supported?
Okay, thank you for the question. No, right now we don't have any, I mean, the dislib does not have any implementation of neural networks, but it can be integrated. I mean, that you can use other solutions like Tensorflow, or we are collaborating with a group in Valencia that is developing a library called EDDL. So you can combine the dislib, for example, using the DS arrays for the data set, and then you can invoke with PyCOMPSs or with the dislib, you can invoke the neural network. So the integration is quite easy, but we don't have any method right now of a neural network. And in principle, it was not the objective because there are a lot of well-known libraries that are available right now with this purpose. So we were not going to focus on this right now.
There's another question by Vishan Kumar, who is asking, how is dislib compared to TensorFlow in terms of the speed?
Well, this is a bit related to what I said before, because TensorFlow focus more on neural networks, so we have not compared with TensorFlow. So I don't have an answer right now about this. You can move back to the directory. Well, I need to go to mine. Okay, so we will go now to the hands-on. Okay, the first thing I would like to ask you is to update the notebooks. Please, from the you can see that I am in the tutorial apps folder. Okay, so those that downloaded the notebooks and all the examples of the tutorials before, if you go to this folder, then you can do this command git pull origin stable, because there was a small modification. Okay, I will not do it again because I did it already. Okay, so if you can do this first, then I will continue with the hands-on. So then after this, we will use also the Jupyter and the Donecker. I forgot to say this, well, maybe. For those that you look later at here to the quick start of dislib also has the option of installing another application, which is it's called dislib, and it's very similar to the PyCOMPS player that you already installed. Okay, but you don't need to do this, because already in the Docker image that we are using, the COMPS tutorial image, we have dislib installed. Okay, so we will use the same command that Javi was using before to start the PyCOMPS. So PyCOMPS init -i COMPS/COMPS tutorial to the tape. Okay. If you've done this before, it should be fast. Well, I will not start. Well, I will start the monitor. If you want, you can start the monitor. Maybe I will. I don't know if I will use it. Okay, but it will be started, and I will start the Jupyter server. Okay. Okay. So remember, you can use this address or the other one that Daniele was telling this morning. In some cases, you need to use slightly different. And then, well, I have in my case, I'm using localhost, in fact, directly. And from here, you go to Python, notebooks, and syntax. Okay. So it's the same. So this morning you were using hands-on, Javi, or syntax?
Yes, this morning we were using hands-on. Okay,
then you need to go to the syntax folder, okay? Because I will be using notebooks only in the syntax folder. And the first one that I will use is the 9 dislib demo, okay? 9 dislib demo is the first that I will use, okay? Okay, so the beginning of the demo, in this case, is very similar to what you did in the morning. Okay, you have some links here that you can have a look, but you don't need now. Okay, so we can start the PyCOMPS runtime. Okay, similarly as you have been doing in the morning. Okay, then we need to import dislib, in this case as DS. Okay, and well, we have here some example on the use of the DS arrays. Okay, so remember that this array is a two-dimensional array and has the characteristic that divides the original two-dimensional matrix into blocks. No? For example, here we have an initialization using a random array. The total size of the matrix will be 500 by 500, but is decomposed on blocks of 100 by 500. Therefore, how many blocks will have the DS array? So in each dimension we have 5. Okay, so 5 by 5. Okay. So in this case, if you can print the shape, that could say that is 500 by 500. Okay, and then if you try to print the whole DS array, it's not going to print it. Okay, but it's going to give you the size, the shape, okay, and the register. This would be is the block size. Okay, and then it may have this other can be different if you are defining a non-regular array. If this was 510 by 510 in blocks of 100 by 100, you will have some blocks that will have a different shape. Okay, for example. Okay. So next, what you can do? You can access, for example, the blocks. Usually we will not access the blocks, but if you want, you can do it. Okay, so in this case, the block 0, 0. Okay, and if you try to access it directly, it says that is a future object. What it means that is a future object? So a future object is a given data that is available on a node, but if you want to access it, you will need to synchronize the value. Okay, so you can do this, for example, with the collect. The collect will internally invoke the COMPS wait on, and then you will be able to print the value, for example. In this case, is the whole array. Okay, but you can, if you try now, again, the X blocks, now it gets you the value. Okay. Another way of defining these arrays is directly using arrays like Numpy Arrays. Okay, so you have here an example of 2 rows by 3 columns, and you're asking it to store in blocks of 1 row by 3 columns. Okay, so this is another alternative. It can also create these arrays from sparse data in CSR format, for example, in this case. Okay, so in this case, the block size will use also the sparse data storage. Okay, in order not to use the whole memory that is needed for the non-sparse version. Okay. And you can use the same method, collect, to get, and in this case, it tells you that the size of the matrix, but that is in CSR format. Okay. Okay. So next, I will stop sharing. I see a lot. I listen a lot of noise, so maybe I have some network problems. So we will now load data. For example, we will use this load Svm light file. This is a type of data format that is used in this case on this Csvm library. Okay. In this case, you need to tell it the number of features, the number of columns, and the block size. Okay. So using this case, if you look at the shape, in this case, the data has 61 samples, rows, and 780 features that will be the columns. And this will be organized in shapes and blocks of 20 by 100. Okay. Another example is with the CSV format. Okay. That you can read it as a text file directly. Okay, then similarly to the different functions that you have in Numpy for slicing data and accessing the data by rows or columns, you can do the same with the DS array. But you need internally, this may generate some PyCOMPS tasks, for example. So we create this array first of 50 by 10, okay? Sorry, 50 by 50 in blocks of 10 by 10. We can check the shape. In this case, sorry, if we are looking into a single row, the fourth row, and asking the shape, so it has one row and 50 columns, okay? You can collect a single element 2, 3, for example. Well, this value can be different for each of you. And then you can access different sets of rows or columns, For example, if we are accessing this 10 to 20, this is accessing the rows 10 to 20, 10 to 19, in fact, okay? So in this case, the chunk that we are getting will have 10 rows and 50 columns, because the 50 was the original size of the array that we created. You can access the columns. Here, if you put the 2 points, it's accessing all the rows, and these 10 columns from 10 to 19. You can access non-consecutive rows, like here, for example, just the rows 3, 7, or 22, or some non-consecutive columns, like 5, 9, and 48, okay? So, well, if you run this box, also you will see the shapes, I was telling you, 10 rows, 10 columns, 3 rows, and 3 columns, Or you can have a subset, okay? In this case, the subset that is from row 0 to 4 and from column 40 to 45, for example. Okay, and you can have also operations like compute the mean for axis 0, for example. So it computes the mean and collects the result in this case, or transposing the matrix, okay? The collect is always collecting the results, because if not, we will get this message that it is a future object, okay? Okay, so this is a part of the data management. I don't know if there are questions, Javi, at this point.
It seems there are no questions.
Vale, perfect, thank you. Okay, so now we will go into one example that it's completed, and then later we will go into another notebook where it's not completed, and you will have to guess the content, okay? So first, we start using this make blobs function from a Cascade, okay, that will generate, in this case, 1,500 samples, organizing you will see that when we print it, that creates these blobs are kind of clouds of points. Okay, and well, this is an initial value to set the initial random state. Okay. So in this case, you get both the samples and the labels. Okay, so the samples are vectors, and the labels will be numbers that represent the category. But in this case, since we are going to use the k-means, we will only use the X array. Okay. So if you plot the data, you will see in this case we plot with using the matplotlib. Okay. And you see what I was telling you. No, in this case, it's the same blob I was showing you in the slides, where we have like three groups. Okay. So before using k-means a dislib function, we need to convert the data into DS arrays. Okay, so this X and P is an Numpy object, but it's not a DS array. Okay, so you can convert a Numpy object into a DS array using this array call. So you pass as first parameter the array, and then the block size, in this case 300 by 2. Okay. This is possible in this example because the data, the Numpy array fits in memory. Okay. But there can be use cases when you cannot do this. You cannot create first the Numpy array and then convert it to DS array, but you will need directly to create the DS array. Okay, either by reading from files or using other ways. Okay, because if this Numpy array does not fit in memory, your application will crash. Okay. Well, we create the DS array. Okay. It converts into a new organization. In this case, in blocks of 300 by 2. The original shape was 1,500 points of 2 dimensions. Okay, so if we split it, what we have is 5 blocks of 300 by 2. Okay, then you can instantiate the k-means. In this case, we will tell the clustering algorithm to find 2 clusters. Okay. We will discuss a bit later if this makes sense or not, but you instantiate and pass as parameter these 2. Okay, this is only instantiated the data, and then we pass this. We need to pass to the fit this X that is the DS array. Okay, we can fit it. Okay, and we'll give some outputs. Okay, about the result. You can also print the centers. Okay, you ask for 2 centers, so you can find the data about the position of the centers. Okay, and then you can use, in this case, is using the same data to predict, which usually we will not do it. Usually we'll use new data to predict. Okay, but we can do it. And we can plot the result. Okay, in this case, we use the plot scatter. No? Remember that I told you, no, that we defined the problem with 2 centers. No, do you think this clustering makes a lot of sense? Because we said that we had kind of three blocks, no, 3 clouds. Okay. So maybe now you can try to, what would you do to change this and to make the clustering work better? You can modify here directly if you want. Okay, so if you want, you can go here, modify and put 3, and we run it again from here, instantiate again the problem, but now with 3. We run again the fit. Okay. We can print again the centers. Now we have 3 print centers. We predict again. and we plot again. Now it's better, no? So, well, we will see this later when we compare k-means with dbScan, for example. One of the drawbacks of k-means is that you need to know in advance the number of centers, okay? But for this case, it's doing very well, no? So it's predicting well when we set it to 3. If you want to rerun it again, you can go back and run it with 4 centers. I don't know. It will not make sense again, but you can check what happens. No, if you change it again, you need to rerun from the instantiation again with 4, for example. You do again the fit. Now we have 4 centers, and you run again. And again, it doesn't make a lot of sense, no, because it's dividing again this blob into 2 groups. Okay. But with all the different examples that we have, you can do this all the time. Okay, you can rerun them again and check again the results and see if they look better or not, or you can try different options, whatever. Okay, and so we will now go to the 10 dislib. You changed it, Javi. It was 10.1 or 10.2, no sé.
Yes, it was 10.1 and 10.2, but I changed it to 0 and 1 to follow the order.
Vale, okay. 10.0, dislib exercise blanks. Please open this one with blanks, because if not, you will open the one with already the solutions, and the idea is that you try to solve the examples, okay? Okay, so at the beginning, it's the same. Okay, so I will start it with you. I will guide you through the hands-on, okay? We starting the runtime, and also we start importing the dislib. On the beginning, I'm reusing that same initialization of the data, the blobs that we were using before for the k-means, okay? So this, you just repeat it the same, and now we will play a bit with the dbScan, okay? So now we will try to do the tutorial with this dbScan, okay? It's another clustering algorithm. So one of the differences is that here you don't need to give the number of clusters, although you need to give it the epsilon and the mean samples. Okay, we will play a bit with this. But if you want to guess the values, also you can look at the documentation. So you click cluster dbScan. Okay. So if you don't give any value to eps, it will use the default 0.5. So if you want, we can set it to the default for the moment. And mean samples, if you don't give any value, it will use 5. So if you want, we give it 5 also. Okay. And so with this, you instantiate the problem. Okay. Next, can you try to guess how to fit and predict for these labels, the labels for X, right? Okay. You can look here which methods can be. You have the fit and the fit predict, okay? But here is saying fit and predict, okay? So you should use this method, okay? How can you try to do it yourself? Well, if we look at the guide, okay, it will be the name of the instance, no? In this case, we call it dbScan, so dbScan dot, and the method fit predict, okay? And as parameter, has a simple parameter, which is the data set, no? In this case, the DS array for which we want to learn, so X, okay? You can then, after this, you can run it. And you can do also the plot. Well, here, how well it went. Well, it's not going totally perfect, no? Because we have some points here that are a bit far away, okay? So then you can try to change the epsilon. If we set it to smaller, you can then rerun it again. Now we see more purple, no? Okay. If I do it even smaller, 2.1. Now it's better. So if you see this epsilon, so we had the drawback before, no? Of k-means, you need to give the number of clusters, no? But here also, if we, sorry, no, this is worse because we have the same color all the time, no? So if we have the same color, it means that it thinks that is the same cluster. My fault. If we go back, oops. We started with order 5. This was better, no? Because here we could see 3 different colors, no? Maybe we should try to increase the number of samples. Let's see if this works better. But still, no? I don't know if it was, if we do larger, no? Let's try to make it larger, 1. Okay, now almost, no? We have still some elements outside. No, this is worst. I was running the other day with 1 and 12 and was running well. Well, probably this is the best one. It's epsilon 1 and mean samples 12. Then it has some points that is not able to cluster into the same one, okay? But you can see here, no, the importance of being able to set these parameters correctly, okay? Okay, now we will try with another data set. The make circles is where the blobs. Now we have another scikit-learn data type of data generation that makes circles. Okay, it's like a different circles, one inside the other. Okay. Well, I did not plot it here. You will see after. No? So now try to find the solution to create the DS array, to create estimators both for k-means and dbscan. If you want for k-means, you can look at the previous notebook where you had the solution. For the dbscan, you have it here. And then, well, this is the creation and then the fit predict. Okay, and then we will plot the results. I give you like 5 minutes now, so because there is a bit more of work. You can go into the different documentations, both for the k-means, you have it here, and for the dbscan, and for the k-means, if you go from the demo, you have also the link. I thought it was here. Okay, well, if not from the website, if you go to the index and then you look for it in the K, you have k-means and you find it. Okay. Okay, so well, first we need to create the DS array, no, for this NumPy. So it's the same case that we saw here in the k-means when we were making the blobs, no? And we were converting this XMP into a DS array. Okay, so basically we give the name of the array and the block size. I will use the same block size, for example. Okay, so you can do the same. You can just create a DS array from X and P, and the block size. If you want later, you play with other sizes. But we can use the same size that we had before. Okay. Okay. So this will convert this other data set, the circles, into this array. Okay, and then we need to instantiate the estimators, create estimators. For the k-means, we saw the example before also, no? For example, we had it here, k-means, and within 2 clusters if you want again also. And for dbscan, we had the example here, no? Well, I can use these same parameters. Maybe later we can play a bit. Okay, and then we call the fit predict. Well, this is, we have the dbscan first, but you invoke the dbscan fit. Well, if you already checked it before, no? The fit predict, passing as parameter the array x, and the same for the k-means. Oops. Okay. Did you try anything else different from this, or more or less you tried this? Well, we tried to see what happens. So we ran the 2 models, and then this code here is trying to plot the results. Okay. And on the left we have the dbscan, and on the right the k-means. What do you think? Is this more or less fine, or what would you have expected? No, this is the data set, 1 circle, and in the middle another. No, so none of them is doing very well here. But for the k-means, I already tell you that it's not going to improve. So if we set to 3, for example, and we run it again, it will divide the circle into 3, but it will not be able to identify this external circle as a difference into the internal one. But the other one is, for example, we set it to .1. Let's see if now it's able to do it better. Now you see the dbscan, no? When we change it, the epsilon, which is the distance between points that takes into account, okay? Now it's able to differentiate between this circle here and the circle outside, okay? So depending on the data set, one algorithm will be better or worse than another. No, the k-means was doing very well for the blobs, but is not able to find good solutions for this other data set. Okay, while the dbscan is able to find better solutions. Okay. Okay. One second. So now I don't know if you can hear me still. Yes, I think so.
Yes.
Yeah, well, that one of my well, eventually will work. I'm trying to change my. No, it's not working. Okay, it will work, I guess, sometime. Okay, now we will turn into another type of estimators, the ones that we can use for the classification. Okay. In this case, we will use a data set which is in scikit-learn that have some representation of images of handwritten digits. No? So the handwritten digits is from 0 to 9, and each of the features of this data set represents a pixel in an image. Okay. So well, you do these load digits to load this data, and then you have the data. You will have the data in X, which will have almost 1,000, almost 800 samples, each of them of 64 features. Okay, and in Y we will have the samples, the labels. Okay, so which number is represented by the sample. Okay, so this is the size of X and P. Okay, is what is set here. Okay, and then, for example, if we take one row, you are taking one digit. Okay, But if you print the result, is not clarifying a lot what is represented. But if you plot it as an 8x8 matrix, okay, because these handwritten digits are taken from 8x8 pixels, okay, and you plot it, for example, in this case, well, it's not excellent quality, but depends on the handwriting, no? But if we look at the label, okay, it's the 3. So this is a 3, okay, you can see more or less, okay. Okay, so we will play with this data set, but since the original data set has 10 different labels, we will try to simplify it into a binary classification problem. So we will transform the labels into only zeros and ones, okay? 0 for odd numbers and 1 for even numbers, okay? So we are changing the Y data set. And now if we print again the same label, now the 3 is even, so it's a 1, okay? And we will try to classify this data, okay? First, using the Cascade Svm and also the random forest classifier, okay? And in this case, well, we first split the data set into the training data set and the test data set, okay? Sorry, here, trainings data set and test. This function from scikit-learn decides the data set into 75% for the training data and 25% for the test. Okay, so you run here this split, and now you have the data split. Xtrain and Ytrain have the train data, the samples and the labels, and in Xtest and Ytest we have the test data. Okay, in this case, we are giving you less input, no? First, we ask you to convert the data into this array, but you need to convert first both the trained data, for which you have the code, and the test data. And then you have here, they're asking you to do the classification with the Cascade support vector machine. You have that API here, no? From here you go the Csvm, you go to classification and you have the Csvm, and also from classification here you can go to the random forest classifier. Okay, so have a look to the API and complete the 2 boxes. The first one is quite simple because it's similar to what we have above. For the block size, you can mimic the same if you want. And then try to do the part for the classification for the Cascade Svm. And this part for the accuracy, if you want, wait for me, but try to do the first part in here if you want. Do this part, the creation and the fit, and then I'll tell you how we do, how we check out this accuracy, because it's a bit tricky. And then later I will allow you to do it for the random forest. So I give you 5 minutes to finish these 2 boxes, the one for completing the DS array and the one for the Cascade Svm, and then I will allow you to do the random forest alone. Okay. So we will start with first with this box. Here, what we need to do is basically convert the XDS test and the YDS test into DS array. No? And we can do it similarly to how it's done for the train arrays, no? But of course with the corresponding data. So if it's going to be the XDS test, should be the it's the Xtest data, okay? And then the block size, I suggest that we use the same size as for the training. So 300 by 64, and we do the same below for the Y array, okay. So the Y DS array, it comes from the Y test, and then the block size, in this case, it has only one column, 300 by 1, okay. So I guess this was not very complicated, okay. So, and then next what we need is to create the Csvm, the Cascade Svm estimator. So if you look into the API, so it's Cascade Svm, okay. Well, we did it also before. No, no, sorry, we did it in the example, okay. And the Cascade Svm here in the example, for example, we are not giving any parameter, okay? So you can instantiate just without any parameter, or you can give a value to gamma, okay? By default, it will use 1 divided by the number of features, but for example, I will use gamma equal 0.1, okay? But if you just put it without a parameter, was also a good option, okay? And then we feed the estimator. So we invoke, which is the fit. So the fit, you look at it, you have the fit method. In this case, you don't have fit predict, you have fit and later predict. So you cannot do both at the same time. So we do the Csvm. Sorry, Csvm.fit directly. And as parameters, you need to pass both the train data and the train labels, okay? Because it's in a classification problem, you have both the data and the labels. So you need to pass, in this case, both the X and the Y, but of the DS arrays, no? The XDS train and the YDS train. This for fitting. And then the accuracy. The accuracy is the score, okay? You can see here this function, which you pass it. I think there is an example here. No, sorry, in the example you don't have it, but you can look at the how well the accuracy, how well is the build has been the model, okay? So you pass it to it a test data. In this case, we can call it score equal Csvm on score, and then you pass the test data, okay? Both the samples and the labels. Okay, and till here, it would be probably quite intuitive, no? Here there is a small point, and maybe I inserted this import to make it a bit more clear, okay? But if you run it here, well, and I try to print the score here, for example, sorry. Okay, look, no, when I print the score, it says that it's a future object, okay? That is why I add here the comps wait on as a hint. So we need to wait for this result with the comps wait on. And well, we can either do, for example, it was this and then a score, which will print it. This is an option. Okay, so the accuracy is not very good. We will solve this later. Or another option that is the one that is in the solved version. you have this other one option that you print directly the result. You use the print to print it, okay? So you can run it this other way. Yes? If I'm going too fast, just let me know. I don't know, maybe everybody has reached this point before I go ahead. I cannot see you, so. Well, I hope you are able to see this, okay? And have you been able to run it yourself? An option is this gamma, no? The gamma, it says by default is 1 divided by the number of features. So if we had like, how many? Set centers. Probably we can try a smaller, maybe with, although this is part of the rest of the exercise, okay? If we do a smaller, let's see if we improve the accuracy. Yes, exactly, no? But I will move it back to the original factor because this improving the accuracy is part of the second exercise, okay? So leave it with gamma equal to 0.1, okay? Okay, so now can you do the same for the random forest? So the same box as we have here. You will not import, you need to instantiate, run the fit and get the score. Okay, it should be easier now. You don't need to import again the COMPS weighton. No, now it's already done. Only once in every notebook. I give you like 3 minutes because I think it's not very difficult, this one. Okay, so we will finish this one. So first you need to import the classifier. So again, from this lib classification, import random forest classifier. Okay, for this, for example, you got sorry, it's here. Oh, there is no example here. Sorry. Okay, well, too bad. I should add it. Well, then we can create the instance. I will call it RF. Okay. So do we need any data? Well, you have different options. Okay. In this case, I will not use anyone. I will just use the default ones. Then I will run the fit, and it has the same format as before. You need to pass both the train and the samples and the labels. Okay. And for the score, you can do the same. Okay. You can call the rf.score with so you can see here you have also the score function. Okay, both passing the test data. Okay, it's test. So these two were very similar. Okay? And then you can print COMPS on score. Vale. Okay, and you see now the accuracy for this one, which is working better. Higher is better. Okay, so this second is better. Okay, the last part, it would be about, sorry, some people maybe was copying. I go always very fast. I give you a bit more time to stop to finish copying this. And we move into the last part, okay? It's about hyperparameter optimization. No? I mentioned before this type of methods, in this case, the grid search, that you can invoke it, and then you get it runs internally the different models with the different parameters. For example, no, if here I'm passing to the Cascade Svm, I'm passing for the gamma these values and for the C these values, and it does all the combinations, for example, or it depends on the method. It will do all the combinations, or depends, others will explore some. Okay, so I will do the solution for you because this takes a while, okay? And so we can speed that a bit. It's grid search, COMPSs, and then you pass the method, in this case, Csvm, and the parameters. And you do the fit with the train data. So, okay, I will run it because it takes a while, and in the meanwhile, we can go into the API and see how this works, okay? So first, we defined this param, okay? In this case, two different sets of parameters. For the gamma, you remember before, for the Cascade Svm, I was using .1, and then when I tried with .01, was improving. No? Here we are giving 3 different values, okay? And then for the C, I was not using anything for this parameter C in the Csvm. But if we check, the parameter C is a penalty parameter, okay? That it's able to see if some solutions are better or worse than others, okay? So in this case, if we look to the classification, if we go to grid search, so the grid search is like a meta method, okay, that you use invoking an estimator. So the first parameter is always an estimator. So it can be the Csvm, but it can be the k-means. For example, you can try it later with the k-means and the blob data to see if it finds the 3. No? Then you can pass a set of parameters, okay, and other optional parameters. No? You have here an example. In this case, it's with a random forest, for example, passing other parameters. In this case, the number of estimators or the range, okay, for example. So always you pass this, an estimator and a set of parameters, okay, and then you can get the results. Okay, let's see. It's still okay. It already finished running for me. Then you can print it. In this case, we are using this pandas data frame to print it a bit nicer in the form of a table. Okay. So here you have the different combinations of parameters that have been tried with C1, with the different gamma values. So in fact, it has been trying all the cases by all cases. So it's doing the 3 by 3 cases in this case. Okay. And here you have the accuracy, the score for the different combinations. Which is the better? This one, no? That .98. So then you can go back to the Cascade Svm and use these values. No? If this is the beta, C equals 100 and gamma equal 0.0001, and you can rerun this. Okay, and now you see the accuracy that before was 0.51. Okay, now is 0.98. Okay, which is better than the random forest, for example, although we didn't tune the random forest, no? Okay, so with this, we finish the session, okay? As I told you before, if you go to to the same syntax folder, you have this dislib exercise solution, which is a possible solution. I don't remember it. I think it's more or less the same solution that I put it, but the nice thing also is that you can play again with the one that didn't have the solution, and you can play trying different parameters or using different data sets. Of course, if you are using the Docker image, take into account that it may explode if you are using very large data sets, but has some flexibility. So you can play it here a bit with all these examples if you are interested. Okay. Okay, I don't know if there were questions. I did not ask.